Thank you, Miad. It's a great pleasure to be here. I've been attending the Pedestrian Evacuation Dynamics conference for a long time. I think my first one was in Switzerland, Zurich. That was the first one that I attended, and after that, I've been continuously attending. And yes, like many, good colleagues and friends that I've met, I met Miad TRB, and I have a transportation engineering background, and my PhD is in transportation engineering, but my master's was in computer science, and I've worked a bit in software industry as well. I did my postdoc in EPFL, and my PhD was from University of Toronto here in Toronto. I am currently an associate professor in transportation engineering, civil engineering department, and I also have a Canada Research Chair in disruptive transportation technologies and services. And today's presentation, it's kind of a collective work that I've been doing for the past 5-6 years related to the pedestrian automated vehicle interactions and how we are using virtual reality to understand and try to develop our general understanding. So with that, I'll start. First of all, this work is based on these several papers that we have published over the years. Hopefully, Arash Kalatian is in the audience or not, but he finished his PhD here at Ryerson with me, and now he is postdoc at University of Leeds, ITS Leeds, and also Rafael Vasquez. He did a master's, and he's now working for IBM. We also have Anna Subhani. She was a postdoc with us, and now she's a professor at University of Utrecht, and also my dear collaborator Elizabeth Kirky, who is a professor at Newcastle University. So with that, I'll start. So this is a very typical scene that we see in downtown Toronto near Ryerson. This building that you see, that is Ryerson's building, and next to it is this intersection that is full of pedestrians walking, and you can see that every pedestrian is walking differently and is in a completely different state, and the whole dynamics there is very complex, and what we see this is a daily occurring in these sort of urban centers, and at the same time, well, if you don't account for COVID, pre-COVID, and hopefully post-COVID, it's the same as well. But at the same time, if you look at what is happening in our mobility and vehicle technology, it's getting more and more automated, and as it is getting more and more automated, we see its implications. Good and bad, in terms of safety, in terms of convenience. There's a lot of research that is going on in terms of how they can be used for increasing the safety, increasing the convenience, and so on. Similarly, network throughput, new mobility services have been developed around it. Similarly, there's a lot of research on developing mobility patterns and so on. But at the same time, we are interested in looking at their implications on pedestrians. And if you look around, what is happening today is that we see these sort of news happening. For instance, on the left, it came from 2019 when Vienna started its AV shuttle program, and the first day a pedestrian was hit, a distracted pedestrian who has their headphones on and wasn't paying attention, and the whole program had to stop. On the right, you see that I think from 2018, where a pedestrian was jaywalking and was hit, and unfortunately the pedestrian died when an Uber autonomous vehicle vehicle or self-driving vehicle hit it. So these sort of things you see, and then it makes you wonder what is happening, and we try to understand the underlying processes that are used to actually train these vehicles. And we see that these vehicles, they, like any intelligent machine, they learn from examples, and the more examples exist, the better these machines can learn. So making sure that we have ample examples related to pedestrian behavior, pedestrian walking, and so on, that would ensure that these vehicles would learn better and perform in a safe and amicable manner among pedestrians. So the primary source for these sort of training has been, or giving examples, have been through video being recorded on the roads by test vehicles. So it's more like a naturalistic data that is available, and that data is unfortunately unlabeled, as it is coming from videos. So most of the time they have to be labeled. Most of the labeling work that is done, it involves object labeling, as whether it's a pedestrian, whether it's a fixture, whether it's another car, and so on. And it might be some level of semi-automatic process, but companies like Tesla and so on, they've been hiring people in India, in Nigeria, and so on, to do these sort of manual labeling. And what happens is that not all the situations are available. Just because, first of all, you need to make sure that all sort of conditions are being covered, and then you have enough resources that you can label such data. Another option that is going on is simulation-based training. And in simulation-based training, simulations of movement of different objects have been used to train vehicles. I've had several conversations with companies who are specifically working on pedestrian sides, and their models are very simplistic in nature. They may use a constant speed for pedestrian or so on for training. At the same time, companies like Lyft, Waymo, and a couple of other companies, they have actually open sourced their labeled data. So this gave us a very good opportunity to actually go into the data and see what kind of information is present, how the data is, and so on. So that's exactly what we did, and we looked at these particular data sets. Nuisance, Lyft, Waymo, and Pi. So first three, they are more like in a commercial-oriented settings, and the last one, it's the data set that has been exposed by a research group at York University here in Toronto, and we went through their data set, and we primarily selected these data sets based on having the similar kind of sensors as you would find those sensors in an AV as well. And if you look at these sensors, we see that nuisance has more, about 80K pedestrians have been annotated. Similarly, Lyft 25K, and Waymo about 2.8 million pedestrian annotations been available. This particular Waymo that we looked at, we did not include the latest edition that they did, but even the earlier data set that they released, it also was pretty rich. In terms of duration, every data set had a bit of different duration. Similarly, in terms of environment, some had maps available, some did not have maps. So for instance, Waymo or Pi data, we don't have maps available. Similarly, in terms of the time of the day or conditions like rains and snow, in some cases it's available, in some cases it's not. But pedestrian annotation, it does not mean that there is an interaction going on between the pedestrian and an AV or a pseudo AV. So making sure that we look at instances that have actually some interaction going on between pedestrian and AV, we came up with some heuristics and made sure that there are cases where a pedestrian is crossing and the vehicle is also moving, or there is some level of interaction going on. And based on that, we looked at a subset of data. And when we looked at the subset of data, so in that case, we see that in each of the data set, we have somewhere between 137 to 23,000 instances where we can call that, okay, this is the data that is giving us information about pedestrian and AV interaction. Now, having that, when we look at this sort of scene, clearly there's not enough data, there's not enough instances, there's not enough examples to actually, make sure that we have AVs trained on very complex sort of urban situations where pedestrians have more freedom to move. And if we look at the current interactions between a driver and a pedestrian or a vulnerable road users, we see that there is a lot of anticipation going on, and that a driver is always anticipating what a pedestrian or any VRU will be doing, and there is always an eye contact. Whenever you're crossing a road, before crossing the road, you make sure that there is an eye contact between the driver and the pedestrian, and there's an understanding. There's a silent agreement between the two that, okay, now the pedestrian can move, and the driver tries to slow down. And driver is considering many things in their head. They are considering the safety of the vulnerable road user. Not just that, they are trying to look at the comfort of their passenger. If they are braking too hard, the passenger may have a whiplash. And at the same time, they are also looking at what is the effect on the traffic behind. If they are braking very strongly, the vehicle behind them will have to brake, and so on. So that it has an effect on the traffic as well. So there's a lot of things there are a lot of things that are going on in the driver's mind as well. So replicating this problem, or all this processes that are going on in AV, it is a very difficult problem. And the tasks that are involved are in this sort of situation is that the AV has to anticipate what VRU will be doing in terms of whether they're going to cross or not, and if they are going to cross, how would their trajectory look like? And based on that, then they would take actions that would ensure safety and comfort of the VRU as well as the passenger inside the vehicle. So making sure that we can replicate it, and to replicate it, there is a strong need to actually understand the behavior of these pedestrians who are not static, who are not just moving objects, but they have a very strong behavior, and making sure that we are aware of the context that is going on. So embedding this in an AV that may result in a better performance for them. So that's what exactly we do. What we did was that we looked at a very simple problem. Instead of starting with a more difficult problem, we looked at a very simple problem in which a single pedestrian is going to be crossing the road, and the road has AV operating on it, and within this simple space, and it's such that it is a mid block, and within this space, what we are looking at it is that we are dividing different decisions into three different actions, actually. So the first is whether the pedestrian starts to move or not. So that is represented by A. And once they start moving, then what kind of trajectory would it look like? And that trajectory is denoted by B. And then the third point is the action that is needed from the vehicle, and the vehicle should be able to anticipate in case A whether the pedestrian is moving or not, and if they are moving, then how their trajectory would look like. It is able to predict that, and once it is doing that, then it can take certain actions. In this case, we brought in a rectangular box, a meter left or meter right, or certain amount of space on left and right, so to make a safe box. And the vehicle is able to respond to such that it is not encroaching into this safe box. So this is a very simple model that we very simple conceptualization that we brought in, and with this conceptualization, then we in parallel, actually, we also have been developing a virtual reality setup, which we call VIRE, Virtual Immersive Reality Environment, which lets us do very controlled experiments based on scenarios that we can develop. And within this scenario development, we have virtual environment projection system on the left that brings a respondent in a virtual environment. You see there are two people. One is on the driving rig, and the second, a pedestrian, has been crossing in virtual environment. Then the responses that we are getting from it, we are tracking their movement, any decisions that they are making, and that is being fed to the simulator itself. It's a multimodal simulator in which we have different virtual objects. So if it's a virtual car, that virtual car will be operating through a calibrated intelligent driver model. At the same time, if it's a virtual pedestrian, it is going to be walking using a social force model, and so on. And all this data has then been collected, and this data can then be used to train the AV as an agent. So we are basically bringing in human in the loop to train an AV. Here's just an example. You see here how a pedestrian can be involved. On the left, the person is involved. They are walking. On the top right, there's a small window. It's one of our earlier versions of the VR environment. We have further improved now, but the pedestrian can walk, and we know where the pedestrian is looking, how the pedestrian is moving. We also can put in some other sensors. So the pedestrian on the left, their right hand has a GSR sensor, which is the galvanic skin resistance sensor that is measuring the stress level, relative stress level for that particular pedestrian. Similarly, on the right, we see that there's a pedestrian who is playing a game on their smartphone in VR while crossing, and we are trying to look at a situation where a distracted pedestrian is trying to cross it. Internally, it looks something like this. We have been improving our VR environment, making it as realistic as we can. Current level is depicted here. So some of the scenes have been actually developed through commercial collaborations with companies like Immersion for certain projects, and others they have been developed in-house. So one of the experiments that we did in that we looked at the recent literature in terms of what kind of variables that are important to consider and what kind of variables are going to be changing in coming future because of the adoptions of AV. And we came up with a list of them, the most important ones. For instance, speed limits. There have been talk that the speed limits can be increased or decreased, or lane width as well. Lane width, there's a talk that the standard lane width can be decreased as the AV come in. Similarly, there are braking levels, minimum gap, for instance. Then the flow rate can be changed as well, and also some other variables that we thought would be of interest. So we use these variables to actually collect a very large scale data collection campaign. Here we decide on the levels based on, so the middle row would be the typical characteristics of a typical road in Toronto, so 40 kilometers an hour, 2.75 meter width, and so on. So these are the typical state of a typical road in Toronto, and then we brought in some higher and lower level around it as well. With that, we collected about 180 individuals, data from 180 individuals. They went through several experiments. Each pedestrian was doing at least 4 different experiments and so on. And we developed that such that we are able to collect data on pedestrians within the university setting. We went to a public library in a suburb of Toronto, which is Markham. We also went to the city hall in the city, as well as in the north. We also went to a summer school to collect data from younger audience. So that was a pretty rich data set that we collected, and we developed a de-optimal design behind so that we are able to efficiently collect data on the variables that are of interest. First thing that we noticed right away was that as we are bringing in automation, we see that the wait time before pedestrians start crossing the road, it increases. So when there were no AVs, we see that the wait time was about 6.2 seconds, and as 50% mix is there, that increased to 6.9 seconds, and with 100% it is 7 seconds. So clearly the changes in the vehicle mix that resulted in the changes in wait times, and we were of the view that this lack of this eye to eye, this silent agreement that is happening, that not having a person in the front seat in driving seat that is in control, that has some effect on the wait time itself. If we look at the trajectories of individuals, you see that there was a big heterogeneity there as well. While they are waiting, in some cases, pedestrians would be looking left, right. So the arrow, it represents where the pedestrian is looking, and so in some cases, the pedestrians were constantly looking left and right. In some cases, they would look around, then wait, then look around, and so on. And similarly, when they are crossing, some pedestrians, they would walk. While walking, they would be looking around. Others, they were not looking around. Similarly, if you look at the one-way versus two-way traffic. For instance, on the left, you see that a person is looking around. They try to find a gap and start walking, but they realize that's not big enough gap. They go back and then start again. Of course, it's a one-way traffic, so they are only looking at one side, but in the two-way, they are looking both ways. And where they are looking, you see that as the one side is they're crossed, they start looking the other side. So all this information is such that it's a very useful information, and it could be used in our modeling work, as well as I'll show in later slides. So coming back to our initial abstraction, so the data that we collected, then we said, okay, let's try to use this data and see how we can actually develop these models and what insights can we get from these different models. So first model that we looked at was that how we can develop a model for whether a person starts moving or not, so the point A. For that, we looked at a prediction model that would give us the wait time. How long the person waited until they started moving. We used a classic hazard model to actually model that. And we came up with some variables of interest out of 40, 50 variables that we had. We were able to incorporate these variables in there in the model, and the positive value would represent that they have a shorter wait time, a negative value. Sorry, the other way around. The positive value would represent that they have the positive value would represent that they have a shorter wait time, and the negative value would represent that it's a longer wait time. If you look at these variables, they are interesting variables, but they are still they still don't have the kind of variables that we can actually gather from our VR setup. So, and the reason that we found out was that this linearization here that wasn't able to capture the kind of complex interactions that are going on among the variables. So we changed this to a deep neural network and estimated or trained our models again, and we saw that we are able to improve our model much more than the initial Cox proportional hazard model, but now what we see is that we have improved the model performance with about 17 variables. So you see that in total, if you just use a vanilla DNN, you would be able to incorporate 47 variables, but do we need all of them or not? So we looked at some feature selection, and we saw that even with 17 variables, we are able to improve our model much better compared to the other two. So what does that mean? We have a better model, but we also need insights. We need to know what is happening in there. So for that, we used a particular method that is based on game theory, and it tries to classify the effect of each variable by using a Sharpe value. So here the red value would be positive, and the negative value would be blue, or a smaller value would be blue, or a red value would be high. So here now we are able to bring in much more variables. For instance, how is the mix of the flow, whether it's a partially automated condition or a fully automated condition. Similarly, for instance, lane width, traffic density, whether they are walking or not, and so on. And the effects that we see is For instance, fully automated conditions, the values are mostly on the negative side. So this results in a longer wait time. Similarly, we see that other variables can also be explained through this process, and they also could let us know which variable has more important role to play than other variables. We can also get their mean and standard deviation that we developed from here, and based on that, we can actually comment on the effect of, say, snow, effect of nighttime, and so on pedestrian wait time. So now we can actually explain what is happening in the model itself. Other thing that we did was that, okay, so we have whether a pedestrian can start moving or not. Once they start moving, how would their trajectory look like? So if you look at most of the literature, they have used LSTM sort of models, which is great. You are using previous trajectory to predict the next trajectory, but there is a lot more involved there. In the sense that there are other objects, for instance, a vehicle there, and the vehicle speed that matters as well. Not just the vehicle speed, but whether that vehicle is coming towards the pedestrian or going away from the pedestrian. So bringing in more contextual information, other factors like road type, whether it's a one-way or two-way, whether how are the weather conditions, time of the day, lane width, the congestion level, and so on. So all these aspects are also very important, and so the data that we have, we can actually develop models that can bring in this information as well. So what we looked at was that we developed auxiliary LSTM and for trajectory prediction that would not only take the previous positions as input, but things like head orientation, or the AV's position, or auxiliary data like road type, speed limit, and so on, to actually predict the next position. The framework looked like this, that we had these continuous data, so the time series data. So for that, we had these LSTM layers, but then we also brought in the auxiliary data, and in the end, we had a dense layer that was then outputting the trajectory for the pedestrian. Then we also looked at whether this prediction should be distance-based or time-based. So distance-based would be, given that we have one third of the pedestrian trajectory, let's predict the next 2/3. Or given that there is half of a pedestrian trajectory, let's predict the next half, and similarly the other way around. So, and we looked at, we compared the performance of vanilla LSTM with our auxiliary LSTM. And in general, we see that we are producing a lower error. The error here is in meters, so at somewhere between 32 to 23 centimeters error that we are introducing in the trajectory. We also looked at the time-based performance, and in time-based performance, we looked at given the previous time step, we predict next time step, or given the previous time step, predict the two next time steps, or the other way around, given two previous time step, we predict the next time step. Again, we see that we are performing better than the vanilla LSTM that is just using the previous trajectories to predict the next. If you look at the the plot over time. So the left one, it is distance-based, and the right one, it is the time-based. In the distance-based, we see that in general, the vanilla LSTM, it is able to follow the true trajectory pretty well, and we see that as the time goes by, the auxiliary LSTM deviates from the true trajectory. But in case of the time-based, we see that the auxiliary LSTM, it is able to follow the true trajectory pretty well, and on the other side, the vanilla LSTM, it deviates from the true trajectory. And in practice, if this were to be implemented in say an AV, the time-based, it makes more sense. So in that case, our proposed LSTM is able to follow much better the true values. Having said that, we also are interested in knowing what variables are important and how are they contributing towards the error in the trajectories that we are predicting. So we see that weather conditions, for instance, in snow condition, we are actually increasing the error in our prediction. Similarly, the time of the day, if it's night, not very good visibility, again, that would increase the prediction error, and there are other auxiliary variables that we defined. So all of them, they are contributing towards the performance of the model. So our earlier hypothesis that the context, it is very important to bring into the prediction rather than just using the previous positions of a pedestrian to predict the next. So that justifies through this interpretation work. Then now that we have a model that can predict whether a person can start moving or not, and we have a model that can give us trajectories as well, and now we would like to train an AV that can take these models and is able to react to the situation and see how it performs. And we take a very simple case, where the job for the vehicle is to stop or not. And what we are trying to do is that to change its acceleration or deceleration based on how the pedestrian is behaving. And for that, we used a reinforcement learning framework where we are using a particular type of learning proximal policy optimization, and within that, the key here is the way we define the reward. The way we define the reward is that the red part is what is specific to the pedestrian. Specific to the pedestrian, the comfort of the pedestrian and safety of the pedestrian. And the second part is what is specific to the passenger. So the second part would ensure that the braking is not that fast, not that severe, that the pedestrian, the passenger is not in discomfort or is not getting a whiplash or something like that. So with that, we trained our system, and I'll just show one of the results that are there. So here, what we look at is that we look at this the velocity, the jerk, and the deceleration, so in first case, we see that the blue, the blue is with the passenger comfort being brought in, and the orange is without. And we see that in both cases, we are able to train our model, but then in case of bringing in the passenger comfort in as well, we see that the value for jerk, it is much lower. At the same time, in both cases, we are able to stop the vehicle before that safe block, and so in this case, we are able to achieve both objectives in the sense that the pedestrian is feeling safe, comfortable. At the same time, the passenger is also feeling comfortable and is not in discomfort or getting a whiplash. So with that, I'll give you a bit of concluding remarks in terms of what we have done is that we have been looking at the acceptability of AVs in urban areas. We want to make sure that that increases by bringing in the contextual awareness in AV, and we are doing so by making it more intelligent in form of that it can anticipate the VRU behavior much better. And for that, we have been using virtual immersive reality based digital sandbox in which we can create a range of experiments in a very controlled and safe environment. We have been using multi-objective learning that can predict VRU behavior and is reacting in a continuous action space. And we think that this is very useful for both OEMs and municipalities. OEM can implement some of these models in their software stack, as well as they can actually learn from these experiments in terms of what variables or what features are important to be collected. And all these features that we actually looked at, we made sure that they could be collected from the resources that an AV has. So if AV has access to a digital map, they would be able to know what kind of lanes there are, whether it's a one-way or not. AV has cameras, so it can track where the pedestrian is looking, how the pedestrian trajectory is. So all these variables they can actually observe and incorporate in their system. And similarly for municipalities, all these policy changes that they want to bring in, all these design changes that they want to bring in, they can use some of the insights that we developed in guiding their changes. In terms of moving forward, we are looking at currently we were only with one pedestrian. We are trying to move towards multiple pedestrians. We have been updating our VR environment such that there could be multiple respondents simultaneously in the environment, and also looking at things like social conformity. We have a big project going on that involves researchers from University of Newcastle, and we are going to be soon starting to collect data in Newcastle as well as in Toronto, and the focus there is on social conformity aspects, and also looking at the leader and follower behavior. We are also looking at how we can identify different measures, suitable measures that can substitute eye contact. So for instance, could there be a message board on the vehicle that is giving them instructions in terms of whether it's safe to cross or not, or we are trying to look at different treatments in that respect. Also, a joint model that can look at that can take the data from VR as well as these labeled data that are generated by the vehicles. That is something that would further improve our understanding. Looking at the VRUs with needs, people with the blindness or people who are on disability scooters and so on, bringing them in this research research, that is something that we are interested in. And also cases where pedestrians are occluded. We've been working with a couple of companies that are using smartphones to generate signals for the vehicles that make sure that even if they are occluded, they can be seen. There is a strong role for smartphone and 5G in this, and we are exploring these dimensions as well. With that, I would like to acknowledge that this research has been sponsored by the Natural Sciences and Engineering Research Council of Canada through their Canada Research Program and Discovery Program. Also, the CFI, which is a specific fund for acquiring equipments for researchers, and also the Economic and Social Research Council of United Kingdom that is sponsoring part of the research. With that, I'll conclude. Thank you very much. If you have any questions, please feel free to ask.
Thank you very much, Bilal. That was great. Lots of work. Well done. So audience can put their questions in the chat. I think we already have the first question from Nikolai. Thank you for the talk. I totally get the importance of this, and it's really nice work. I wonder, though, how realistic it is that AVs will enter city centers anytime soon. The issue is that if AVs are good enough in avoiding accidents, then pedestrians can always stop them and cause traffic jams by confidently stepping into the road. I'd be interested to hear your thoughts.
That's a great question. So first of all, I'm of the view that AVs today they are not ready to enter the dense urban spaces. They may be ready to enter in form of a very slow moving, the shuttles that you see that have maximum speed of 30 kilometers an hour. But if you want to have a vehicle that operates in the same manner as a normal human-driven vehicle, I think we are far from that. And this work is basically an effort to make them prepare further down the road, and this work is a very small piece of work for that, and we need a lot more effort, a lot more research there. Then there was a comment about, sorry, the last part, there was a nice comment as well. Can you please repeat?
The pedestrians can always step in and stop an AV.
Yeah. Great. Yeah, so this is a great comment, and we actually looked at these experiments that we were doing before starting these experiments. We had this hypothesis that especially younger kids, teenagers, they are actually going to think it as a toy, and they are going to start playing with it. And we actually saw this in our experiments. There is one video that is associated with one of the paper as well. If you could, if you get a chance, please see that. So a teenage pedestrian would come in front of the AV, and the AV would stop. Then they would, go back a bit, and the AV would start moving. So they would come again in front of it. So they were trying to look at it as a game. So these are the things that could be avoided through, say, education, through different rules, through legal frameworks and so on. But our job is to identify these things and understand the implications of it. And you're right that if a vehicle is been stuck in this sort of loop with a teenager who has tons of time and they are bored, the implication is that there will be a shock wave going backward, and the whole system will be congested. So our job is to identify these issues and look at guide policymakers to actually develop new policies.
There is another question on eye contact, which I also had a question. Let me ask first my question, then we'll go with that, with the second question as a follow-up. So speaking of eye contact, how do you measure or how do you observe that eye contact in VR? In reality, you can, can you explain a little bit more?
So the eye contact, we did not measure directly, but if there's an approximation to it, because we can actually see where the person is looking. So the VR, whatever orientation there is, we are able to track that vector. And if that vector is passing through the vehicle, we can approximate that. And not just that, the person is looking at it and they look for a couple of seconds. We can approximate that as a way of saying that, okay, the person is actually trying to see the driver inside the car.
Mm-hmm. So the follow-up question is eye contact really often possible considering the reflections in the windshield? From my non-scientific observations, pedestrians often cannot see the driver through the windshield, but start walking when the driver slows down. Children here in Switzerland are taught to start walking only if the car stopped completely.
Yeah, so these are, I would say, there's another dimension that I did not mention. These are more the norms or cultural norms, basically. When I was in Switzerland, I remember that each city, their escalators, their speed was different based on the cultural norms. So there are definitely these nuances, these cultural norms that we have to consider. But at least here in Toronto, I would say that eye contact, it's a very important piece, and actually that is taught to the children as well, that make sure that the driver sees you. These, I mean, again, that there's so many layers and layers that we need to bring in, but we have to start from somewhere, and that's where we started at the moment.
I have another one until someone else asks another question, if there is any. So in the VR setup, when you had participants in the VR, what information or instructions did you give them, and how would they distinguish if a vehicle is AV or non-AV in that virtual? Was it as an information given to them, or they should have guessed that this is an AV or not?
So I'll answer this part first. So at least for now, we have to give them some level of information. And the kind of information that we give them is visual information. I'll just show you. So in this case, for instance, there's a new experiment that we are designing with these screens as well that would give them messages. So they have here, this written that this is an AV. But the previous experiments that we did, I don't have any screenshot for it, but there what we did was that we put in the LiDAR setup on top, and people are more familiar with that. They've seen, photos of vehicles with LiDAR on their top, so they would be able to differentiate. At the same time, not having a driver here, you see in this case, you could see actually clearly that there's no driver there. That also brings in a differentiation. Then in terms of the experiment, the way we would do is that there would be first a small session in which they familiarize themselves with the VR, with the environment, with the different aspect of the experiment. And so in that 15 minutes or so session, they were able to understand the setup, and within that they were given this information as well, that there are normal vehicles, there are AVs, and the difference can be observed through their physical changes.
Did you also have sound enabled, or was it a silent experiment?
Yeah. So we looked at some. So in this particular case, a busy street. This is in front of a train station. So yeah, train station and so on. So in this case, we actually went there and recorded, and we got some background noise to put in. But in general, all our experiments, they have some background so that it feels much more real.
That's okay. Yeah, it makes it a lot more realistic, I would say, with the sound. So there's another question. Thanks for the presentation regarding AV's behavior in VR. I wonder, should we design the AV as how it behaves in real life regarding its sensors, for example, or should we make it smarter in VR? I think when we talk about VR, another critical issue is about the validation.
That's a great point. So I'll talk about the validation first. So I did not describe too much here in terms of what we are doing, but we have done some level of validation. But there are tons of great research coming out recently on VR validation side, and so there's a lot of work happening through the community in terms of the different types of validity that are involved. So that's one point. And second point is that I think bringing this loop in, whether it's VR, whether it's simulation, whether it's naturalistic data, but bringing this loop in where you are evolving the AV to the evidence, whether it's coming through VR or whether it's coming through some other source, that is more important. So it's and there are two things. One is that in the hardware there's less room for adaptation, but in the software stack there's a lot more room for adapting to the changes, and that's where we come in, and that's where we propose these changes that are in the software stack. So it's a company decision whether to keep. Look at Tesla. Tesla has been a big believer of using video-only technology. They had radar there, but they removed it. Now they're testing LiDAR again as well. So those hardware decisions, they may or may not have too much implication, but the software on top of it that brings in that much more intelligence in it, that is where we come in, and that is where we can guide them through this sort of setup.